Hi everyone, and welcome to lab number 5, which focuses on dilutions and solutions, basically a whole lot of calculations. Now, I apologize. I know that the past few weeks have been, a lot of annoying calculations and problem solving, but this week, this lab is the last of those kinds of materials with a whole lot of math, kind of can get annoying in some of the quizzes and post labs. I understand, but next time we'll move on to experiments like transformation, so you'll get a little break from all of this. Now, I do want to point out that what we cover today, you most likely have encountered or learned in various other courses, such as your chemistry classes, but in the post lab for this week, you have to follow the method that I showed you, not because I'm controlling, but because the whole point of the post lab is to practice the lesson that we covered. And so I want you to practice these particular techniques. That way you have another, skill set in your arsenal of, ways to tackle problems. So please make sure you are using the video guidelines for the post lab. Now, the first one we're going to cover is called the molar solutions. So now that's kind of like in that previous slide when you saw millimolar, for instance. That's a molar calculation that you would have to make. Now, the first thing that I mentioned when we talk about making molar solutions is how do we translate molecular weight, because that's going to play a major role in calculating molar solutions. So when you look at a bottle of any kind of reagent in your lab, it should say the molecular weight on it. If that powder or that item does not say the molecular weight, all you have to do is Google it. Google now has all of the different official molecular weights. Okay? You can also technically calculate it from the periodic table, but that's kind of extra steps. All right? So when we talk about molecular weight, 1 liter of solution contains the number of grams that are equal to the molecular weight. Okay, so basically when you see 1 and a capital M next to it of a solution, that's equal to grams per liter. Okay, but keep in mind that you're usually not making 1 liter or making 1 molar, so in our calculations we're going to adjust for that. Okay, so I'm just going to write this out to kind of make it a little clearer for you to have in your notes. So like I said, 1 liter of solution, okay, contains the number of grams equal to its molecular weight. Okay, so what I'm saying is when you see 1 molar of a substance, okay, that equals grams per liter. Okay, so you'll see it as G over L. Okay. But now, like I said, you're usually not making 1M. But like I said, you're usually not making 1M or 1 liter. So I just want to put this on its own slide so that you remind yourself that fact. And you're going to see in the example that we're going to do next exactly how we adjust for that. The idea that you're making a different molarity and a different volume. Okay? So now we're going to tackle the first example. And so for the first example, I'll say you want to make 100 milliliters of 5 molar NaCl. Okay? So the first thing that you're going to want to do is you're going to want to ask yourself, what is the molecular weight of NaCl? Okay, like I said, you would either get that from on the side of the bottle itself. So if you're in the lab, you would grab the bottle of powder and on the label, it would tell you the molecular weight. Or you would Google it and find out that the molecular weight of NaCl is 58.46 grams per liter. Okay, sorry, let me just erase that. 46 grams per liter. Okay, so that tells you, if I say the molecular weight of NaCl is 58.46 grams per liter, well, what does that tell you? That tells you that you would need to take out of that bottle 58.46 grams of that powder if you were making 1 molar as 1 liter. Okay, so that's the amount you would need if making 1 liter of 1 molar NaCl. But what do you notice? We don't want 1 molar. What do we want? I know I sound like a cheerleader. What do we want? We want 5 molar. Meaning we want 5 times the amount that we would need for 1 molar, right? So you take that molecular weight, which is 58.46 grams per liter, and you multiply that by 5 molar, okay, 5 moles of it. And that would tell you that instead, to make 5 moles, you would need 292.3 grams of NaCl. Now we're still per liter, okay, in order to make 5 moles, okay? But, big old but here. So, but, what did you notice about our problem? We don't want 1 liter. So underline but, we don't want 1 liter. And I'm going to become the cheerleader again. What do we want? We want, what did the question say? 100 ml. Okay? We want 100 ml. So what's 100 ml or milliliters in liters? Well, whenever you see that little lowercase m, to convert it to liters, you just take the decimal. You'd go 1, 2, 3 places over to the left, okay? Because milliliters is a much smaller amount, okay? So you don't want 1 liter, you want 100 milliliters, which is 0.1 liter. If you're unclear how to convert that milliliters to liters and you want me to say that again, just message me and remind, and I'll give you a little practice in going back and forth between units such as liters, milliliters, and as well going back and forth between molar and millimolar, because it's the same thing, okay, that moving of the decimal point. Okay, so we said we don't want 1 liter, we want 0.1 liters. Okay, so we take that 292.3 grams per liter from a second ago, okay, and we multiply that by the volume that we want, which is 0.1 liter. Okay, so the final answer would be, in order to make our 100 ml of a 5 molar NaCl, we would need 29.2 grams of NaCl powder, okay, in 100 ml solution, okay, to make 100 ml of 5 molar, okay? Now on the next slide, what I'm going to do is I'm going to show you that we could actually do this all at one shot. Okay, so like I said, you could do it all at one shot, one step. You can take your molecular weight, which is 58.46 grams per liter, and remind yourself, you're not making 1 molar. What are you making? You're making 5 times that. Okay, so that's molecular weight first, then we're doing molarity, and then you're not making 1 liter, you're making 0.1 of that volume, okay, 0.1 liter. So you multiply the molecular weight by the molarity that you want to make, and then multiply that also by the volume you want to make. And that would give you that same 29.2 grams of NaCl. And what you would do, you would volume up to 100 ml with water. Now notice, whenever I do these problems, I will always say a volume up to the total volume that you want. Why don't I just say you would measure out that 29.2 and add 100 ml of water? Well, that would ruin your calculation that you just took the time doing. Because if you're just throwing 100 ml of water on top of that grams that you just weighed out, well, you forget that those grams have displacement of that water, okay? So the calculation you did was to make a total 100 ml of solution. If you add 100 ml of water on top of the 29 grams of NaCl, you'll notice that your total volume is above 100 ml now. So we always say volume up, which means you would take the 29.2 grams of NaCl, you would put it in your container, and the containers usually on the sides are graduated, meaning it's not that they went to school, it's that they wrote on the side where, 50 ml is, where 100 ml is. So you would then pour until you reach the 100 ml mark with the powder in there, okay? Because you want the total volume after everything to be 100 ml. If any of that is unclear, as always, please contact me in the Remind app. Now we're going to move on to the next calculation in this lesson, which is percent solution. Now I laugh whenever we get up to this one because every semester I tell students that this is the easiest solution. Please do not mess this one up because it is so easy. You don't need molecular weight. You don't need anything crazy for this one. All you need is the question itself. And yet every semester, this is the question that most students get wrong. They'll get the crazy complicated questions correct, and then percent solution they'll get wrong. So please pay special attention. When you do percent solutions, first I want you to break down the word. Notice per cent. What does percent mean? Percent is the same as saying per 100. Like if you've ever heard of centi, right? Centinel, centimeters, 100. Okay, so 100, it's per 100, which can either be, you're making per 100 ml, it can either be grams per 100 ml or milliliters per 100 ml, depending on whether you're dealing with a powder or whether your reagent is currently in the liquid form. Okay, so whenever you see percent solution, think either grams per 100 milliliter or milliliters per 100 milliliters. Okay, so as an example, if you wanted to make 0.7% solution of agarose, okay, we're going to go over that in a few weeks. Agarose is basically the gel that we put DNA into to run a DNA sample and separate out DNA sizes. So agarose basically looks like a slab, a rectangular slab of jello, okay? So you want to make 0.7% solution of that agarose. Well, what does that tell you? 0.7% tells you that you need 0.7 grams of agarose for every 100 milliliters you're making. Okay, so if you're making 200 ml, 0.7% agarose, what would you do? It would be 0.7 grams plus 0.7 grams. Okay, because that's the first 100 ml and the second 100 ml. And that's going to give you 1.4 grams of agarose for 200 ml. Okay, you do not need to know the molecular weight or anything else. Now, I'll be honest, sometimes your professor is kind of cruel, and when she gives you these problems, she will write in the question what the molecular weight of that reagent is. But the moment you see percent, cross out, scribble out that molecular weight. You do not need it. Okay? Now, there's technically a formula we could use to solve these problems for percent, but I first wanted to show you that if you ever forget how to do it, just remind yourself percent and do it based on 100 ml increments. If instead you needed 50 ml, what would you do? Well, you would cut that amount in half, right? Instead of 0.7, because that's for 100 ml, you would only need 0.35 grams for 50 ml, okay? But now we're going to show you a quick formula as well. So, like I mentioned, using that concept of what percent means, you can also use the formula where you simply take the percent and multiply it by whatever you're trying to make, so the volume you want to make, per 100 ml, because we said that's the definition of, what you're trying to do with percentages. Okay, so for instance, using that 0.7% example, if you wanted to make the 200 ml that we mentioned, you would simply multiply the 0.7% times 200 ml desired amount, okay, divided by 100 ml. And that's exactly what we said to do before, because that's the same thing as doing 0.7 times 2, which gives you 0.4 grams of the NaCl that you would need in order to make the solution. Sorry, not NaCl, whatever you're making, if you're making the agarose, for instance. In the other example I gave, I said, what if you wanted to do the 0.7, but instead of making 200, you wanted to make 50 ml. So you'd put your desired volume on top, and then you would say per 100 ml, okay? And notice when you do that, that gives you what we solved for before, which is half of the 0.7, so 0.35 grams is what you would need for that one, okay? percent can be anything. It doesn't have to be 0.7%. I could ask you 1%, 2% of, reagent A. And all you would need to know is what is the percent? What's my desired volume? And you simply do whatever the percent says. It could even be 150% times the desired volume over 100 ml. Okay? If you have any questions on how to do percent, again, feel free to contact me in the Remind app. Okay, now it's going to get a little bit scarier, but still very doable as long as you just follow the steps that we kind of map out. So another big thing they end up having to do when you work in a lab is diluting from a stock solution, because a lot of times you're using the same reagents over and over in that lab. So it's kind of cheaper and easier to just keep a very concentrated stock solution in the lab that each person can then make their own diluted bottle from. Okay, so we're going to use a particular formula to solve this kind of problem. Whenever you're diluting, you want to use the formula CI VI is equal to CF VF. Okay, now I know when you first see that, you're like, okay, that means nothing to me. So as always, I like to write out what they actually mean. Okay, so on this side, we have the initial concentration. So CI stands for concentration initial. So initial concentration. And that's a fancy way of saying the stock solution's concentration. You then have VI, which is the amount of stock solution needed to make your dilution. So the amount of stock needed. That then brings us to the other side of the formula. So CF means concentration final, which is the desired final concentration. And then VF is volume final. So again, that's the final volume of the desired solution. Okay, so notice that the first half of this formula is focusing on your stock solution, and the second half is focusing on what you would like to make from that stock. And usually I do the hand gesture of, pipetting out of one container and pipetting toward the other to help remind me that the pipetting away from the left, so that's going away from your stock solution and into what you're finally making, because that's ultimately your goal here. Now notice you have a lot of different parts to this formula, but you will be given 3 out of the 4 in the question itself. Okay, this will become clearer in the next slide when we go over an example of how to use this formula. So here we have our example. We're going to say I have 1 molar tris stock. Okay, but I do not need 1 molar tris stock. I need 100 milliliters of 10 millimolar tris. Okay, millimolar tris. So we're going to, in order to do this problem, have to use the formula. Now you'll notice that in the problem, like I said, you'll be given 1, 2, 3 out of the 4 values of this formula. Okay, to remind you the formula, it's CI VI equals CF VF, okay? And ultimately, when you do this problem, I want you to note you must match units on both halves of the formula, okay? So must match units. Now you notice in the first calculations we did today, back when we did calculation number 1 of molarity, you had to use the units of molar and of liters, okay? Now with this dilution problem, you could use milliliters, but if you have milliliters on one half, let's say on the right side with the final information, then on the left side, your volume also has to be in that same unit. Okay, so how would we plug this in? Well, we go one by one through our formula. First, CI is the stock concentration. Well, what concentration is our stock? Right here, it's the first part of the question, 1 molar stock, right? Then we get to VI. VI is the amount of stock needed in order to make our final solution. Do we know how much of that stock we have to take out of the bottle in order to make our final solution? No, that's our variable. We want to solve for VI because we don't know that right now. What we do know is everything about the final solution that we want to make. So we want our final concentration to be 10 millimolar, but hold up. We already used molar as our concentration in the first half. So what do we have to do? We have to convert 10 millimolar into molar. How do we do that? How do you go from millimolar to molar? 3 decimals to the left, okay? So we take that 10 millimolar and we go 1, 2, 3 decimals to the left, fill in that empty space with the 0, and that tells us we want 0.01 molar as our final concentration. Again, if that step just blew your mind and you're like, wait. Why did she just write 0.01? Message me in the Remind app and I'll go through that conversion again, okay? The last point that we need to fill in is our VF, the final volume. And since we don't have any unit yet for our VI, we can simply write 100 milliliters as our final volume. And what that tells us is when you solve for your VI, the final unit will be in milliliters because the left units, for instance, capital M, and the right units, capital M, have to match up. So for volume, if I have milliliters on one side, the volume on the other side has to be in milliliters. Okay, so our VI, when you solve this, you do 0.01 molar times 100 ml. You want to get rid of the 1 m from the VI side, so you would simply divide both sides by 1 molar to get rid of that 1 molar, right? You would divide by 1 molar on that side, and when you calculate that out, it gives you 1 milliliter. On post labs and whatnot, if you don't feel comfortable solving for the final amount or you're worried about getting the calculator kind of input wrong, make sure I see the formula filled in because that's the most important thing I'll look for. If you get the final VI wrong, then okay, you're not that great with calculators, but at least you understand the concept of, you know, how do I solve for VI? How do I use this formula? Okay, if you have any questions on how to tackle diluting from stock solution, please contact me in the Remind app, especially while you're doing the post lab and practicing with problems. Now we get to the really tough, scary one. And that's the fact that in real life, when you're working in a lab, kind of as you saw with our very first slides in this lesson, where I give you a picture of a real, scientific recipe, as we kind of call them, you saw you're not just making one item. Instead, you're following a list of multiple ingredients. So for instance, if you remember in the first one, you had 25 millimolar. Trish, you had percent this, percent that, multiple ingredients. Okay, there's usually multiple ingredients, and there's even usually multiple steps. Because for instance, in the last problem we did, I showed you that a lot of times in a lab, you'll keep a concentrated stock solution and then you dilute it down. What I didn't tell you is, where does that concentrated stock solution come from? You have to make it first. Okay, so a lot of times if you run out of a stock solution, because that's what happens in labs, people don't replace what they're supposed to. If it's out, you have to make the stock solution first and then figure out how to dilute it down for what you need. Okay, so that leads us into calculation number 4, which is how it really works in the laboratory setting. The example that we're going to tackle is as follows. Okay, so you want 200 ml of 1 times TE, okay? But problem is, your lab ran out of the stock solution, the 10x stock TE you use to make that. So we're going to write what you need to do first. Okay, so what you need to do first is you need to make 500 ml of the 10 times concentrated stock with the recipe that is 100 millimolar of tris and 10 millimolar of EDTA. Okay, now if you were working in the lab, you would have to look up the molecular weights. But a lot of times what I'll do is, if I'm giving you a question like this, in parentheses, I'll always put the molecular weights of anything I mention. So molecular weight of tris is 121.1 grams per liter, and EDTA, we're going to use 292.2 grams per liter. Okay, once you make that, notice I said first you need to make the stock, then you need to dilute to make your ultimate 200 ml of 1 times TE. Okay, so we're going to go through this step by step. Like I said, first you would normally, because I gave it in the problem, but I always want you to write it down, that first you would look up the molecular weight of each component. So I'll call them reagent, of each reagent. Okay? And then you would calculate. So we do each reagent separately. We have first is tris. We said the molecular weight, if you looked it up on your bottle, it would be 121.1 grams per liter. But remember, that's the molecular weight, tells us for 1 molar 1 liter. We don't want 1 molar. What do we want? We want 0.1 molar. Okay, because again, whenever you see 100 millimolar, you move the decimal point 3 places to the left. So 100 millimolar tris is actually 0.1 molar, because when you do this formula for molarity, where I told you molecular weight times the molarity times the volume you want, you have to stick to molar unit and liters. Now, in the problem, we said you want to make 500 ml of this solution. So what is 500 ml in liters? Again, move the decimal 3 places. That's 0.5 liters. So make sure you convert what you want, because this is, you want 100 millimolar, you want 500 milliliters. Make sure to convert those to capital M unit and the capital L unit, the molarity and liters unit. Now, tris is not your only reagent. You then would have to do EDTA as well. Okay, so EDTA, for EDTA, you would do the molecular weight of EDTA, which you would look up on the bottle, and you would find 292.2 grams per liter. Again, that's the molecular weight. What do you want? You want 10 millimolar. Move the decimal 3 places. That tells you you want 0.01 molar. And what do we want? We want 500 ml, which again is 0.5 liters. Okay, 0.5 liters. Now, when you do that, you would figure out that to ultimately make that 10x stock, you would need, when you multiply all of these out, it equals 6.06 grams of tris and 1.46 grams of EDTA. Okay, so the way I got 6.06 grams of tris was multiplying the 121.1 times 0.1 times 0.5. That gives 6.06 grams of tris. EDTA, you do 292.2 times 0.01 times 0.5 to get 1.46. And what's the final step? Volume up to 500 ml total. Okay, that gives you the 10x stock, but we're not finished yet. Okay, because now we have 10x stock now, but that big old but always comes back. But we want, what did we say? We want 200 ml of 1x TE, right? Okay, so 1x TE is what we have to make now. If we have a stock and we want to make a diluted version, what do we need now? We need the CI VI equals CF VF formula. And again, you can kind of visualize yourself pipetting. Use your right hand, pipette from your left to your right to kind of remind you that you are taking out from your stock to put into the final solution. So our CI is the stock concentration. So what's our stock concentration? 10x, right? It's always the bigger number. So it's 10x. X is simply a unit that we use in the labs. It's kind of like saying 10 capital M, 10 capital L. It's just a unit, okay? So don't worry about having the X there. That sounds funny. Yeah, the X is not bad in this case. So 10x, what did we say about VI? We don't know. the volume of stock that we need. That's what we're solving for. So you leave VI. You want to make a concentration of 1x, and what do you want? You want a volume of 200 milliliters. Okay, so now you solve for VI. You divide both sides by 10x. 10x, the units will cancel out there. And you have VI, if you can use your calculator if you're unsure of that, or you could just cancel out what looks the same. You would have 20 ml. So you need 20 ml of 10x buffer. Okay, and you would volume up to the 200 mark with water. Okay, so that last part you always put volume up to the final amount, 200 ml mark with H2O. Okay, so never forget the volume up step. Okay. Okay, so you know the drill. Before we get to the post lab, I want you to do a practice problem with me in the Remind app. Well, first you do it by yourself, and then you send me your results so that I can kind of go over it, help you with any issues, and kind of make sure that you really have this down pat. Okay, I know, yuck, forcing you to talk to the professor. I am the worst. All right, so here you have the problem. You want to make 500 ml of a 1.5 molar reagent A in your lab, and you always do that from the 5 molar stock. Unfortunately, there's not enough stock reagent left, so you have to be the one to make 1.5 liters of the 5 molar stock for the lab first, and then you can do your usual dilution from there. Okay? I give you the recipe for the stock solution. So the recipe for the stock reagent is right here. It has 3 different components that you have to solve for and use in that recipe. After you have created the stock, you then have to make the diluted amount. Okay, so you first have to make 1.5 liters of 5 molar stock with the recipe, and then you make your 500 ml of 1.5 molar reagent A from the concentrated stock. Now, yes, technically, you would be able to use this recipe to just go straight into making 1.5 molar reagent A, but that would be very rude, and that is not allowed in the lab setting. So you have to first make the stock and then dilute down. If you just send me making reagent A, the 1.5 molar from the recipe and not from a stock, then I will fire you from the lab that we are working in. Okay, so please write out this problem. You can write out the question, or you can send a picture of the question and then write out how you would solve it. You do not need, if you're worried about the final answers for some of it, you don't have to solve for the final answers. You can just show me how you would fill everything into the formulas. Okay, so for instance, some students will put all of the how to solve for 5M into one formula, you know, map out how they would do it, and then they just use letters to say, okay, I would then take this answer and fill it into this formula this way. Okay, if you're having trouble, you know, plugging things into the calculator. If you get the final answers, that's great too, but ultimately I'm just checking to see if you know how to work with these problems. Never just give me a final answer, because I don't care about the final answers because everyone has a calculator nowadays. What I care about is that you know the concept, you know how to handle the information you're given and how to plug it into formulas, okay? So on a quiz, on a post lab, I'm not giving you the formulas in the question. I'll never write out CI, VI, whatever. You have to remember how to use those formulas on your own when you encounter these problems, because like I said, this is the real world research. this is how we get, our different reagents and all. We'll read a journal article, we'll read a pamphlet from a company, and they'll just tell us, okay, you need 25 millimolar this, 5% this, go make it. Okay, so I want you to be very comfortable with that, because anywhere in the sciences, whether you go to medical field, whether you go to the research world, academics, anywhere in the sciences, you have to be able to do this, okay? Again, with Remind app practice, with post-lab practice, you are allowed to ask me as many questions as you want, okay? This is not an exam. This is not a quiz. I'm trying to help you learn the material at this point, okay? So feel free. If you see this problem and you're like, oh my God, I have no idea what she wants me to do, send me the message and remind, here's the picture of the question. How do I start it? I'm so lost, okay? Don't be afraid to say that, but just make sure when you get to this slide, please take a picture of the slide and send me in the Remind app. Getting old, getting senile, I need to be reminded the exact numbers I use, the exact letters, okay? Make sure, send me this in Remind when you get to it. Do not forget, that counts as part of your weekly assignments. And for the record, so far the class has really impressed me with the information you've given me in the Remind app throughout this semester. Okay, you made it through. Now you just have to practice a little bit more with the calculations in the post lab, and then you'll encounter them again in the quiz. And then we're finally done with this crazy math and crosses kind of, part of the genetics lab. Then we can get into some of the more fun visual kind of experiments, more conceptual as well. As always, if you have any questions, any concerns, need help with the practice or the post lab, again, the post lab is not a quiz. You can ask me for help at any time during a post lab or during the Remind question. Okay, anytime you have trouble with anything covered in this lesson, just send me a picture of the exact part of the lesson that's bothering you, and I will try to clarify. Okay, thank you and have a wonderful day.